meeting, let me some words to you. I will give a presentation of Donald Knuth. Donald Knuth is an American computer scientist, a mathematician. He's a professor emeritus at Stanford University. In 1974, he was the winner of the ACM Turing Award, something like the Nobel Prize for Computer Science. Knuth has been called the father of the analysis of algorithms. Knuth is the author of the work, The Art of Computer Programming. He contributes to the development of the rigorous analysis of the computational complexity of algorithms, popularizing the asymptotic notation. In addition, Knuth is the creator of the text computer typesetting system. Many of us here write papers, use LaTeX, PDF LaTeX, and we are eternally grateful to Professor Knuth for not having to use Word for this work. Ladies and gentlemen, Donald Knuth, one of the gods of computer science. It's an honor for us to present him.
It's an honor for me to be asked, and I wish I could be there in person, of course. It's been actually, I hardly ever am able to travel, and the only time I ever was in South America was 1976 in September when I visited Chile and Colombia, Venezuela, and well, I've been in Mexico also on that trip before going to South America. So it's been a while, but I looked at my diary again this morning, and it brought back one of the things that that I remember saying. Like immediately we arrived in Santiago, my diary said, "We all like Chile." I was with my wife and two kids. So anyway, it's been a while, but now in order for me to know that you're understanding what I'm saying, like, can you wave your hand or something like that? Okay. Because one of the hardest things for a speaker is when you don't know if the people are. I mean, I try to tell a joke, and then if you laugh, it's on. But the sound isn't good enough. I can't hear if you're laughing. So I can see your hands there. That's great. Now, before we get started, this all questions answered. It's a tradition that I learned in the 60s from when I was at Caltech, and Richard Feynman was a friend, and he introduced this tradition in his classes. That on the last day of a class, he would say to the students, "Well, you don't have to come today, but if you come, I'll answer any questions that you have." And you know, I thought this was a great idea because the students are, you know, I'm sorry, my phone is ringing over. Anyway, the students pay good money, and maybe they never got a chance to ask a question. Anyway, so I carried this out then for many years afterwards. Always at my Stanford classes, the last day of class, I would answer any question except on religion, politics, or the final exam. Now today, however, you know, can answer me any questions whatsoever on any subject. Although, why would you want to ask me about something that I don't know much about? And there's no final exam. So, but anyway, the other thing I wanted to say quick is that it was important to me that I asked the organizers not to tell me any of the questions that they wanted to ask in advance. I think it's much better for you to hear how I stumble over a question rather than if I give you some canned presentation. You hear canned presentations prepared things all the time, but this is your chance to hear something that's completely improv, completely made up on the spot. So I think you get more information that way. And now I'm ready for the first question.
Thank you.
Okay, so, okay, we have a,
Thank you for being here. Thank you for your time. My question has to do with the current hype that we're living in AI. Having had the experience of having lived through previous AI winters, do you anticipate an upcoming winter? And if so, by when?
Yeah, okay. Well, so I wasn't able to hear Ricardo's. I think he was the keynote speaker yesterday, right? Talking about responsible AI, and you know I love the abstract, but I didn't get to hear the presentation, and certainly this is a lot different than ever before because. Well, because it's all over all the newspapers and everybody's life and everything, and people are all over the map on whether this is wonderful or terrible or whatever. So I guess I'm not surprised that you asked a question like that. But your question was actually, am I supposed to, is it going to be another winter next year or something like that? I ask you not to ask me to predict the future. That's something that's always been the worst thing is for me to is to be a good guesser about future trend. I remember once there was I was being interviewed by somebody, and she said, I think it was. She was working for ACE. Anyway, she said, Don, what was the most surprising thing that in your career? You know, what did you least expect? And immediately I could name 10, 20 things that surprised me. And then she asked me a question that I hadn't expected. She said, well, what was the least surprising thing that happened to me? What happened in computer science that I actually expected to happen? And I was stumped. I think I sat there for several minutes. I couldn't think of a single thing that I had predicted correctly. So don't expect my predictions of the future to be any good. But on the other hand, I have well, about AI, I decided two things. You know, well, okay, I don't want to duck the question. All through my life, of course, AI has been one of the main pillars of computer science. When I started at Stanford in the 1960s, computer science consisted of three things. One was numerical analysis. The second was programming languages, and the third was artificial intelligence. And computer science was divided into those three parts, and people would ask me which part I was in, and well, I was sort of programming languages, except really that I was writing the art of computer programming, and so I realized that that I had to make up a new word for what I was doing, and that's why I invented this term analysis of algorithms, and so that I could say, somebody said, and I was hoping that there would be some day when analysis of algorithms would be considered one of the main parts of computer science. And in fact, I started to like that term very much, analysis of algorithms. I wrote to my publishers and I said, hey, instead of calling my book Art of Computer Programming, let's call it Analysis of Algorithms. And they said to me, no, that's a terrible idea. Nobody would ever buy that book. So it didn't happen. But I was very glad to see that 20 years later, several books have started to be published called Analysis of. So, well, anyway, artificial intelligence was has always been one of the main things in it, and from my point of view, I never was identified with that particular branch, but it always represented to me the parts of computer science where they were working on the most challenging problems. So instead of working, my admiration was not because I really wanted computers to replicate human beings. My admiration was because this was the greatest source of good problems to work on, and making us expand the envelope, see what skills, what kinds of algorithms we should improve. It was one of the greatest sources of good things, inspiring questions to work on. But I never was particularly interested in actually using the results of the program, just having wonderful problems to work on. Okay, now fast forward to a couple of years ago, when all of a sudden we had programs that were doing things that people had never expected would happen, at least not so soon. So I guess it started when I had an email from Stephen Wolfram, the author of Mathematica and lots of other stuff. And Steve said, Don, you got to really look at this ChatGPT. And I told him, no, you're wasting your time on this. You've got so many other talents. Let other people look at this stuff. But anyway, I started. Of course, I wanted to try it myself, and so that afternoon, as I was biking home, I thought of 20 questions that I wanted to ask to ChatGPT, just to see what kind of answers I would get. And well, of course, everybody has had fun playing with it to see what happened. And I tried to ask. I wrote down all 20 of my questions. I wrote down all 20 questions before I knew the answer to the first one, and I tried to make them orthogonal. Each question was supposed to test a different kind of ability to see what happened. And then, so I gave this to one of our students, and he presented it to the computer, and then I got the answers. Well, it was very enlightening, and if you're interested, you can look this all up online. So if you Google for, I think you can Google for Knuth 20 questions ChatGPT, and you'll get a whole bunch of hits about exactly what the answers were and so on. And I was really impressed by how great it was at faking knowledge. It's really my first reaction was that this couldn't be based on what thousands of users are actually doing on the internet, because it was writing better English than any of my students. And it was too good as far as being able to adopt the style. The facts were usually mostly terrible, but they were presented with such confidence that you couldn't believe that it wasn't telling you something true. And okay, I'm talking too much about this one question. I better wind up. But I do want to say that uh, I myself don't want to get distracted from continuing to work on the art of computer programming. But also this idea of being able to fake it and pretend that you know something that you don't is sort of the exact opposite of the way I live, and sort of against all of my gut feelings. As I can admire somebody who writes well, but I can't admire somebody who's lying, or pretending to pretending to know something that they don't. So I'm torn. But one of the most surprising things to me was that I started to think that science fiction authors have really missed the. There's been thousands of stories written about computers becoming intelligent, and what's going to happen when all of a sudden the world has intelligent robots, et cetera, et cetera. But as far as I know, there wasn't a single story anticipating what the world would be like in the 10 years or 100 years before that singularity happens. Nobody, none of the fictional writers said, "Oh, and here's the way the world's going to be like when we have a million computers that are 1/10 of or 1/100th of a percent intelligent, and that's going to be cheap in order to access something that's partly intelligent." Nobody anticipated that kind of a world, and what kinds of scams and religions and things will be started because of that. Okay, so anyway, I can't say any more much about artificial intelligence since that's not my focus, but I certainly have always been an interested user.
Okay, thank you. Somebody else?
Thank you. I'll stand up for this. First of all, Mr. Knuth, it's an incredible honor to be able to talk to you. I was just curious, given that you're so smart and that you have made contributions to many different branches of computer science, I was just wondering what problems in computer science, or perhaps what branches in computer science, you wish you had more time to work on or to study, or problems that you wish you had tackled.
Okay, well, the harder question would be which parts of computer science I didn't have that. But I didn't wish I had more time to study. The art of computer programming is something that I've been working on since 1962, when somebody from my favorite publisher took me out to lunch and said they wanted me to write a book about compilers, and I said, well, but actually a lot goes into writing a compiler, so I'd like to have some other chapters that develop other techniques. In that afternoon, I sketched out 12 chapters of a book that I thought would be this was 1962. And so here I am, still in chapter 7 of those 12, and I'm 86 years old, and I'll write as much as I can. But anyway, hardly anything that was invented after 1962 was in my table of contents, and so uh, I, uh, I, I guess there are some things that I don't have a good intuition for, and so those things I don't. I'm not sorry that I haven't had time to work on, but things where I that do seem to have my name on in some way. It would be nice to have another few lifetimes in order to, because the number of we're so far from running out of interesting things to do that it's not well, it's not possible to see any upper bound right now. I do think. Well, I know I don't have a good intuition for things like crypto. I'm not sneaky enough. People will think of tricks that wouldn't occur to me, and I'm not very good at geometric things. I'm much better at algebra. I can do things with pencil and paper, but it's hard for me to visualize something in 3 dimensions. I have to make a model or someone look at it over and over again before I start to understand it. So I learned my own limitations. I think some of my students really understand Fourier transforms, and for me, it's a stretch to understand exactly to look at things as waves instead of particles. So I think everybody learns what their own skill set is and adapts. Of all the different branches of computer science, I suppose that the most fun is something that has to do with graphics, because when you have images, all of your bugs are fun, are interesting too. So I kind of envy the people whose lifetime work is in graphics.
Okay, I'm going to move to the other side of the room.
Okay, so hi, Mr. Knuth. It's an honor to be able to talk to you. I wanted to ask you about your an advice, because I'm trying to know what advice would you say to give to a young aspiring researcher that's trying to break through in the computer science field?
Yes. Okay. So it ties back to what I said. A minute ago, that you learn your own skills. You learn what you're good at, and this idea of, sometimes I see a problem that has my name on it, sort of thing, and others it says, well, that's probably somebody else would be able to do that better. So I kind of look at life as a binary search. You try something and you find out that you're fairly good at that. So you try something else and you're not very good at that. So you learn about yourself. My main advice to a young researcher is to understand his or her capabilities and make that the most important thing, rather than than what is fashionable. Don't listen to what other people tell you to work on what you yourself think. You have your own unique combination of abilities, and it's your job to understand what they are and then to use them, rather than to take something that's trendy and try to force yourself into a false mode. I think also you keep exposed to lots of different ideas because your abilities aren't frozen. Keep trying different stuff. But I learned early on that I was never going to be a good soccer player, and I could have kept trying more and more, but I found that I really resonated with computer programming, so that was for me.
Okay. Somebody else? Come on. Oh.
Hi, Donald. We're very pleased to meet you here, answering our questions. I would like to ask you, given the current practices in the industry, most software products do not come with a warranty, unlike products in other fields, such as a refrigerator. I would like to appreciate your opinion on this industry standard and how crucial you believe is to use formal methods in software design.
Yeah, I think it's absolutely important to have as many guarantees as we can of quality. On the other hand, we have to realize that it's impossible to have 100% guarantees on anything, because even in the most rigorous mathematics, well, we have the idea of proof, but maybe our model is incorrect that we're trying to prove, or maybe that there's a mistake in the proof checker, and so we say, okay, well, we'll check the proof checker, but then there might be a fault in that. I mean, there's more and more getting closer and closer and closer to having an absolute proof and absolute guarantee. But I don't think it would be sensible to pass a law that you can never fly an airplane unless it has been proven that it would never possibly crash under any circumstance. So in other words, there's these degrees of accuracy, and I don't know how to get perfect accuracy. So my idea is, but I try to approach it by telling people, well, if you find an error in my book, I pay you $2.56, and this works pretty well. Like people keep sending me places where they've noticed an error, and I get to fix the error, and so every year my books get a little closer to being correct. But and we have, you talk about formal methods. I have all kinds of formulas in there, and I try to check them all with the best software. Just last hour, I got an email pointing out the guy found 3 errors in something that I posted last night. I'm writing part of the art of computer program, the first part of volume 4C, and last night I posted a few new pages, and so now immediately after this talk, I have to go through and change those 3 errors that the guy in Germany just found.
Okay, thank you. Some other question? I'm going to stay here. Okay.
Professor Knuth, I would like to know your thoughts about the current state of affairs on research in computer science, and if you are optimistic about the future of computer science as a science.
Okay, well, I guess I already said that. I didn't see that we're running out of problems, although I do. Let's see. I told you not to ask about the future, but it can be. Well, right now there's so many problems in the world that are frustrating. It can be hard to get excited about all the beautiful stuff that still needs to be done. And on the other hand, I find people who are living in war zones are finding that actually that gives them the greatest satisfaction in life is that they are able to do some, steal some time away from and do some research, which is better than coping with all the terrible problems that are facing a lot of people these days. Okay, but now I think the person who asked the question sounded as if I don't know, he wasn't running into anything lately that sounded like a problem he couldn't stop working on. And I find that, on the other hand, I'm asking questions all the time, and the stuff I'm writing on now, for example, it's related to constraint satisfaction, but it turned out that it's a source of problems. It's almost like having a 1,000 new toys to play with. The question is something like this. Suppose I have one. Well, let's see. One good way is to say it is to study what in theoretical computing we call them gadgets. And so we have some kind of a construction, and we say what other things can I do with this tool? What kind of gadgets can I make out of a certain number of resources? And so last night I'm working on I have a particularly interesting function, and I say, well, what other? I'm sorry, a particular interesting constraint, and I'm saying, well, what are all the mathematical functions that are invariant under this relation? And every relation you can ask this question about, and I find that several times a day I can think of another relation and I suggest another problem, and I find that's really an interesting challenge. So I don't see that that we're anywhere near a death of research or death of research. Earlier this year, I took a month and a half off to write a paper about what I call parades, and I was just sort of in heaven while writing, because every day I was thinking of another natural question that about this concept of parades that I wanted to know the answer to. And if you want to look it up, you can go to my website, and I have a page called preprints or something like that, and at the bottom there's something called unpublications, and you can click on the parades, and you can see why I got excited about this combinatorial construction. You consider the number of ways a certain number of boys and a certain number of girls can line up in such a way that no boy is immediately in front of an older boy and no girl is immediately in front of an older girl. But the ages of the boys and girls don't matter. And it turned out that this led to so many different kinds of mathematical problems that I was in heaven for more than a month, just thinking of more interesting questions about this, and to think it ends with a dozen research problems that I think are fascinating.
Thank
Now,
you.
You might say, well, yeah, but you also have to get paid for it. I'm sorry, I've never understood money.
Hi, Don. It's Ricardo here.
Hi, Ricardo.
It's a pity that you're not here with us, but
Yes.
as you said, don't ask you about the future. Let me ask you about the past.
Oh, good.
So what is your favorite problem that you have worked on, or what is your favorite result? Because maybe they are different.
Okay. Yeah, well, of course, the other kind of question that I should have warned you about is asking about a favorite, because you ask parents who's their favorite child, and so really there are things you like about everything, but there is I guess there was one exception. I remember meeting a potential student at one of the dinners at Stanford a couple of years ago, and he said, "Don, what's your favorite algorithm?" And I said, "Oh, don't ask me what my favorite, because I have so many favorites." But then it occurred to me, I do have a favorite algorithm, and my favorite algorithm is Bob Targent's algorithm for strong components. And so I'm planning to probably in December this year, I'm probably going to give a lecture about why I think that's the most beautiful algorithm I've ever learned about. As far as my own contributions are concerned, I'm glad that I was able to participate with other people in what's we call the birth of the giant component. So you have a random graph, and this means we start out and all the vertices are isolated, and then at random we add an edge between two vertices, and we add more edges, and if we do this at random, a kind of a miracle occurs when the number of edges is equal to half the number of vertices, and all of a sudden, before that, all of the components of this random graph were isolated. They were all trees, small, no cycles, but after. But very soon, it turns out that one component is almost surely much bigger than all the others, and this is called the giant component. And so the mathematics of this was extremely interesting. It went into complex analysis where we don't have the usual law of large numbers, because the it turns out that instead of a saddle point in the function, actually it was a three-cornered saddle point. So not only the first derivative vanished, but the second derivative also vanished, and so the third. So we got very interesting mathematical phenomena that was accounting for this big bang that happens when a random graph evolves, and I worked on that with Thomas Woodchuck in Poland and Svante Jansson in Sweden and Boris Mitchell on the state, and the four of us were really uh, 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 sort of uh, in awe of the mathematics as we're discovering more and more properties of this thing. One of the things that I like particularly is the following factoid. If we look at the entire evolution of a random graph, and we say, what's the probability that there's never more than one component that has cycles? I think it was 87, but it was something like pi over 12, something like that, or pi squared over 12. We have a closed formula for it. And I was probably never happier than when Santi finally finished the proof of that formula. Now, I'm pleased to have been able to also finish a project on music. So for 50 years, I had dreamed of writing a composition for pipe organs, and finally I got to be 75 years old, and I said, I better, if I'm ever going to do it, I better start working on it. And I spent weekends then for 5 years completing the piece that was finally presented on my 80th birthday, and so that was one of the great highlights of my life.
Okay. So, hello, Professor Donald. This is a real pleasure to attend your talk here, and I would like to ask you, what inspired you to become a computer scientist, and who were your mentors?
Yeah, great. So, computer science didn't exist until after I was a computer scientist. I didn't know that I was a computer scientist. But in the 1950s, there was no such word, and I think the person most responsible for the fact that computer science exists is George Forsyth at Stanford University, and he had his name was Forsyth, but he had the foresight to realize that there would be such a field, and he convinced me about it, and eventually invited me to Stanford so that I could be a computer scientist. But there was no name for what we did, but there were people like Alan Turing who had this. Their brain had developed very strong abilities in connection with what we now call computer science, and so to have an inspiration for it, it just turned out that I found out when I was in college, and I saw through the window, I saw a computer and its lights were flashing, and it looked interesting. Somebody explained to me how it worked, and I looked at the manuals, and the manual was very poorly written, and so I could immediately figure out how to do something better than the manual said. Here I was, a college freshman, and I figured I must be good at it if I can do better than what's in the official book. So I got a job during the summertime supplying software to our campus, and we had a wonderful professor there who encouraged undergraduates like me to sit hands-on on the computer. And so there was no such thing as computer science, and I was a math major, but I really knew that I resonated with computing. So as far as mentors were concerned, one of my greatest mentors for analysis of algorithms was Professor De Bruyn. His official name, Nicholas G. De Bruyn, but people call him Dick. And he came to visit Caltech several times, and every time I would get stuck on a problem, trying to analyze an algorithm, I would come to him, and he would tell me how to do it, and that would keep me busy for another couple of years. So Dick De Bruyn was one of my great mentors.
Okay, another question? Okay. Oh, I'm going to stop the call.
Hello, Professor Knuth. I was wondering if ChatGPT and large language models that they are used nowadays by many students in order to do some kind of prompt programming. So by iterative refinement, they develop better and better programs using prompts. If you consider that will improve programming abilities in the future, or if that's gonna not be a solution for better programming style.
Okay, well, I really hate the idea of using programs that you don't understand. But if you can look at the program that come from Copilot or all these other systems and understand what they're doing, that's great. But you have to be good at reading and understanding programs. It could be. However, it's hard for me to imagine that people aren't going to just start using programs that they say, "Oh yeah, this seems to work," and it's going to lead to terrible disaster. On the other hand, I always like to have example programs and that compile correct. I mean, one of the first things that when we had one of the main buzzwords was open source, open access, open and stuff like that, and so I was using all kind of stuff like Sun Microsystems had open windows. And I realized that what it really meant was that when you're writing software with these things, you have to keep 10 books open at the same time in order to see all the different libraries. Programming instead of writing your own program, it became a question of just making magical incantation to subroutine calls, and the subroutines each subroutine would have its own order for the parameters. Sometimes you would put the X coordinate first, sometimes the Y top and bottom first, and you could never get this straight. Right now, there's a part of the C programming book that tells the formats for formatted input, and there's details about what you put before a decimal point, when you're trying to say I want this floating point number to be 3 significant digits, and how do you describe the precision and all these other things. I can never remember that stuff, so I have always turn the page again. But if I have a program like Copilot that gives me examples of stuff that work, that's really a huge time saver. So I'm all for having good something that'll do put together good code in a particular style, but I'm all against doing it blindly and using stuff that I mean, so many subtleties arise, and it's just the opposite of validation in formal methods, which the previous questioner asked about.
Okay, we have one more question here.
Hi, Professor Knuth. Thank you for taking the time to answer our questions. I'm Rodrigo from the University of Montevideo in Uruguay. I wanted to ask you about the relationship between industry and academia. What do you think each one contributes to the field of computer programming? And if you've seen any change in this relationship since you've started your career? Thank you.
Okay, I've never been very good at money, as I said before. When I started my career, however, there was no field of computer science, and my connection to computers was because I was a consultant to industry. So I worked with many different companies at that time, and also, for example, that's when I got to know Edgar Dijkstra, because he and I were both consulting to Burroughs Corporation. And over the years, though my own focus went much more to the university side, and so but at Stanford, a lot of my colleagues started their own companies, and they would, like a lot of the big companies today came out of university professors. I never had a good sense for that myself, so my own experiences isn't extremely relevant, especially because, as I said, I don't understand money. But I'm sure that it's important to have connections with what's really useful to people, and what is only I don't know. Well, how do I say this? I love games, and in some sense, the whole purpose of life is not. You build a bridge so that you can get to the other side and have fun on the other side of the river. You don't build a bridge because it's somehow people say building bridges is really important, but it's really so that you can enjoy yourself, and in some way pleasure is the whole final point. On the other hand, if you're doing something only for pure pleasure, there's something hollow about that too. So industry gives you the perspective of something that really makes a difference to lots of people's lives, and that is. And if you just work in academia and saying what can you do on the intellectual plane only, that's only one part of the picture. So this interplay between the two things is always a source of enrichment. But when I say enrichment, I'm not talking about financial enrichment. I'm in a way, I envy the astronomers. People say, "Why do you do astronomy?" I mean, they say, "I know why you do astronomy, because it's so interesting to know about the sun and all of the stars and all this stuff." But then people say, "Why?" People look at me and say, "Why do I do computer science?" They say, "Oh, it must be because you're really interested in Wall Street and making a fortune, buying an island or something." Well, that's the least important to me.
Hi, Donald. This is Yanis Ioannidis, ACM president. It's great to be here. Do you think it is time to write a book titled the art of quantum computer programming. And if you were to write it, would you do anything different from how you wrote the others?
Well, yeah, as far as I'm concerned, it has almost zero in common with the kind of computing that I understand. It sort of exemplifies the comment I made earlier about what do you have intuition for, and I can understand the definitions of qubits and so on, but I took quantum mechanics and I got credit for it at Caltech, but I never, and I could get an A+ on the exam, but I could never figure out why the professor posed the problems that he did, and I never understood really what was going on. Just the fact that it's called computing doesn't mean that I have any expertise in it whatsoever. And on the other hand, if there is, if it turns out that they're able to solve all these huge problems about noise and really the all the paradoxes of I mean, you know, all kinds of paradoxical things happen with quantum computing, and including this multiverse idea and so on and so on. If somehow an actual machine with lots of qubits can reliably be built, well, this might be wonderful for me because there won't be so much pressure from people won't be inventing so many algorithms that I have to put in my book, and other people who understand this totally different universe, you know, will multiply. Anyway, for me, the hardest problem is to see how much of the sequential computing that I knew in 1962 I can continue to write about before I go senile. And the art of quantum computing, it would be nice if something came along and took the pressure off me, but that's a different world entirely.
Sounds good, thanks.
There was another question. Okay.
Hello, Donald. As a professor, what would you say are the greatest challenges or opportunities towards teaching computer science to younger generations? Thank you.
Yeah, I particularly like the idea of what they call bottom-up education instead of top-down education, and so it's nice to have small devices that the people can understand, rather than to begin with the most abstract things. I think in every science, people begin by learning the concrete things near ground level, and they get experience with this, and then they get older and they see, oh yeah, there are abstract principles, and with these abstract principles you can solve hundreds of problems in the same time you used to be able to solve 2 problems, because you have a higher level of abstraction, and so then they make the mistake of saying, oh, okay, with my students, I'm not going to have them waste their time on the ground level stuff. I'm only going to teach them the abstract stuff at the high level, and I think I can understand why people might think that, but I think when you're teaching students, you've got to start with the ground and not build down from the roof.
Okay. Okay, Marcelo from Universidad Nacional del Sur. As an expert of complexity analysis, what do you think about the relationship? What is your feeling about the relationship between complexity classes, P and NP? What do you feel? Is P equal to NP, or is P included in NP?
Yeah, right. So I don't know a lot about the more advanced complexity classes, but I certainly, I was wondering if anybody was going to ask about P versus NP, and so I, of course, none of us knows the answer, but I'm thinking that if the problem is ever solved, it probably, most likely to me that that it will turn out that P equals NP, but in a non-constructible way. So what I mean is there's a huge difference between saying whether or not an algorithm exists or an algorithm is known. Embodiment, having an algorithm that's been written, that is written down and it's sort of understood that's an embodied algorithm, but the fact that it exists just says that among all the zillions of possible algorithms, one of them actually does work in for all problems in P. So let me try to explain. Right now, we know, for example, in graph theory, there's a wonderful theorem that says that if you have any class of graphs that's closed under gosh, what's the term? You could shrink an edge, or okay. So a word is escaping me, but we have, for example, we have planar graph. A graph is planar only if it doesn't have K5 or K33 as a minor. That's called minor closed graphs. Okay, so there's the great theorem that says that if we have any class of graphs that's closed under taking minors, then there's an efficient algorithm to decide whether or not a given graph belongs to this class. The algorithm, I think it takes cubic time, maybe linear time, but anyway, there exists an algorithm for any minor closed family of graphs. There exists an algorithm to determine whether or not a given graph belongs to that class. However, we probably will never know any of those. Does it have this as a minor? We know an algorithm for that, but we don't know. We don't know what the list is. We just know of all these critical minors. So the theorem says there's a finite number of critical minors, and therefore there exists an algorithm that tests if you're in the class. The algorithm just says, look at the first minor. Is it in? you're done. But we don't know what, we never know if we have the whole list. So the algorithm exists, but we don't know the algorithm. And I believe that there are lots of non-constructive proofs. We know that there's in the game of hex, we know that there's a forced win for the first player, but nobody knows how to win a game of hex that's more than, I don't know, 7 by 7 or 8 or something like this. We have non-constructive proofs that say something exists, but we don't have actually something explicit that we can use. So this might very well be the situation with respect to P and N. There exists an algorithm, but even to know the exponent, it'll be n to some power. But even to know what that power is, we might only know that there exists some integer for which it's that one time, but we won't ever even know what the integer is. And that is, to me, it is quite a likely scenario. And if so, nobody will ever be able to prove that P is unequal to NP. And also, it's not going to help us any if somebody does prove that there are only finitely many obstructions to having such an algorithm. To me, it just means I have to be more careful when I say when I talk about P versus NP, and I say, well, either I know an algorithm that doesn't polynomial time, or it's NP complete, and that will still be a meaningful concept if I only know some algorithms, although the fact that they exist is different from the fact that they're known.
Thank you. The next one.
Hello, Professor. Again, this is Ernesto. I have more questions here. What is your favorite programming language? And the second one is, do you speak more languages? How many languages do you speak?
Okay, so
natural language.
Yeah, unfortunately, Spanish is not one of them. I was hoping to actually learn Spanish. There was a plan that I would spend a sabbatical year, 1977, in Santiago. But it turned out that at the last minute, I learned about the typesetting systems that, and I had this big problem of how to get my book published because printers were no longer able to use the fonts that had worked for the first editions of my book. And so in February of 1977, I learned about the existence of digital typesetting machines and reduced the problem of typesetting to a computer science problem from the problem of metallurgy. And so I realized that I really wanted to solve that problem, so I had to stay at Stanford that year. And as a result, I didn't learn, I didn't really learn Spanish. Now, your first question was, what's my favorite programming language? And I said to that I didn't like to talk about favorites, but I do have a favorite algorithm, I said, and I definitely have a favorite programming language. It's called CWeb, CWEB, and it's a combination of C and TeX. And my wife will tell you that she often hears me coming out of my office saying programming in CWeb is such fun, and I don't know how my life would be anywhere near as good if I wasn't using CWeb all the time. It's a combination of C and text. So I'm writing in English and in a natural language and a formal language, and alternating between the two. And if you haven't ever heard of it, well, take a look at my book, The Stanford Graph Base, because it has 30-some small examples of why I love programming in C-Web.
Okay. Okay. It seems that I have to be the bad guy here. Even if we love to talk with you for another hour, I think we have been quite enough of your time. So I propose just 2, perhaps 3 more questions. And that could be a lot. Okay? So, okay.
Hi, Professor. Luis Olcina from Argentina. And I would like to ask you about paradigms, programming paradigms, from procedural paradigms through object-oriented paradigms and aspect-oriented paradigm lately. What do you think this? What do you think about this evolution of languages that are represented in paradigms? What do you think about this evolution? Is enough to represent the different situation problems currently? Are something missing? Are something missing about languages and paradigm to represent actual problems? What do you think about this?
Yeah, okay, well, I personally, okay, certainly when we talk about something like quantum computing, it's completely different. And there are many other aspects of when we talk about parallelism and so on, but the things that I know best myself are sequential programming, and for that I fell in love with the Simula language in the 60s because it was the first time when it is now sort of the birth of object-oriented programming, which and I look at it as in terms of coroutines where we have many cooperating processes. They call each other, but they stay alive between the calls, and so it works as a. And Bob Floyd had this very nice metaphor for that kind of programming, where you had a lot of individuals that would each be responsible for certain tasks, but they would call on each other. So I have my favorite mental picture for the kind of programs that I understand is what I call coroutine, cooperating coroutines, and so it goes beyond recursion to have more like what in old days of alcohol we call own variables and things like this. But the idea. I'm trying to think of where I might have expressed this idea, but I may never get around to finishing volume 8. But I'm sorry, chapter 8. But that's the first thing that strikes me with respect to your question. That kind of paradigm of thinking of many independent processes that send messages to each other is the most important in the applications that I understand.
Okay, next one. The second last.
Hi, Professor. I would like to ask you, in retrospective, which development in computer science had surprised you the most?
This was what I said was okay, so I suppose it has to be the scale of everything. I spent the first 20 years of my life not knowing a megabyte of maybe 30 years of life, not knowing that a megabyte of memory was there. And then I lived for a few years with operating system. We had a computer that had 20 megabytes, but the operating system used 19 megabytes. And so, so now, when we have terabytes and petabytes, it's very surprising to me for sure. And it's not only the space; it's also, of course, the speed. So it's very. When I see tech running, it used to take I don't know 20 minutes to typeset the entire tech book. Now I can do it sort of almost I hit carriage return and a book is done. So the enormous orders of magnitude improvement in speed and space has to be the most surprising. In connection with algorithms, I have surprises all the time, but because we used to think that all the important data structures were invented before the 1980s, but now I still keep hearing about new things. I recently read in the ACM Communications about some of the work that's being done in Latin America on like graph databases and things like that. One of the things mentioned was a ring structure that was new to me.
Okay, so the third last, okay, Ray, one electronic guy is going to ask a question.
Hello, Professor. My question is, I would like to know if at any point did you feel frustrated with your research project or consider to drop everything and start fresh with a new topic? And how did you manage that? Thank you very much.
Okay, well, yeah, so my life hasn't been entirely rosy, and I went through a time, I think it was about 1990, when an entire year had gone by and I had only advanced the art of computer programming by one page. And I said, this is not sustainable. So I had better decide to retire. And so I retired at age 55. The deal I have at Stanford is wonderful. That is, I have an office. I have a secretary. I can swim at the pool and use the libraries. I don't get paid, but I still I have lunch twice a week with faculty and students, and I can give a lecture, and they broadcast it and archive it. So I have, but that year before I made the decision to stop getting paid, I was having some problems, and I found out that that's when I learned, for example, that swimming was very good for me. Before that, I had understood that exercise was good, but I never had time for it. Anyway, life is is very complicated, but the rewards have been there, and all the time. I've never suffered from a lack of friends or stimulation.
Okay, so thank you so much for your time, for your wonderful answers, for coming here without a net, like an acrobat. He said, I don't want to know the questions. I like the surprise. And personally, I wrote to you last year, and in 10 minutes, we set up this meeting, the time, the day, with 8 months anticipation. So, as I said on Monday, the most prestigious people are the humble ones at the moment at becoming and talking with us. So please, thank you.
Thanks for the wonderful questions. And I hope the rest of it really be very productive.
No se vayan, no se vayan.
Recording stopped.
No se vayan, que hay cosas más, hay más cosas acá. Esto no termina. Pasamos de la emoción al baile. Tengo que buscar a los bailarines porque no les avisé.